First of all, thanks for joining this session on container native storage for OpenShift with Red Hat Gluster storage. I don't want to intimidate you with this many presenters on this slide because not all of us are presenting. So originally, when I submitted the abstract, we had 2 presenters on it. But as it turned out, there are more folks who know more about this solution than I do. So it's better that the people who know more about this speak about it rather than me try to make stuff up. So that's kind of why you see those 4 people. But I'm not going to talk for too long. My name is Sayan Saha. I run product management for Gluster and the container native storage solution with OpenShift. And I'm going to do the introductions and let the people who actually know stuff about this talk and not me. So I have with me Dan Mezer. He is a technical marketing manager at the storage business unit in Red Hat. He likes to call himself the slide guy, but he has a Photoshop license, which I don't. So he makes our slides, but he's also a very accomplished person in terms of doing a lot of work with CNS lately. So you'll hear right from him as opposed to me who just reads slides and makes slides. Then we have Michael Adam. He is actually our engineering manager for the container native storage project. So he actually builds this stuff that you guys would like to use. I don't do anything. He is the one who is running the team. Both Michael and Dan are based out of Germany. So they have come a long way to present this. And we have Annette, who is also in the storage business unit in the reference architecture team. She works on creating reference architectures with container native storage. We published an AWS with OpenShift and container native storage reference architecture this summit on Tuesday. It was Tuesday? Yeah, Tuesday. And she wrote a bulk of it. And then we have Ryan, who is sitting in front of us. He actually helped us put all of this together. In terms of Q&A, Ryan, you want to show your hand so that people? Yeah, he actually writes all OpenShift reference architectures, and this one is just one thing that he did. So we have a lot of very qualified people speaking today, and we have demos. They're very cool demos to look at, so you get the concept. It's not just all slides because all slides get really boring. So we actually have some stuff that's real now. So in any case, so that's where I we'll have Q&A at the very end because we have a lot of material to go through. 45 minutes is not going to do justice to this session, believe me. But if you have questions, please catch us after the Q&A, when we do the Q&A at the end, or if we run out of time. I know we are between lunch and flights and stuff. Catch us in the hallway. And we have some cool Bluetooth speaker giveaways for best questions. So we'll have the Q&A, but a short Q&A at the very end. So with that, Dan, you'll take over first, and then drive from there.
Thanks, Sayan.
Thanks.
So as Sayan alluded to earlier, we have just recently completed the work on the AWS for OpenShift and container native storage reference architecture. That's something that Annette, Ryan, and me did. So my hands are still shaking from that exercise. Actually, it took us quite a long way to get there, right? So when we did first hear about containers becoming mainstream, I think all of us thought, OK, this is going to be for stateless workloads, right? So that's what all of us thought up until the inception of containers. Because, frankly, stateless is easy, right? You throw away the stuff and you recreate it somewhere else. And that's very easy to do with containers. What's actually very hard is stateful workloads. And I think reality has caught up on all of us, made us realize that, at some point, we also want to containerize stateful applications, right? People want to containerize databases in the end. And this demand is only going to be fueled by the type of architecture that we see on platforms like OpenShift deployed, which are microservice architectures. So what you do in a microservice architecture is you take your monolithic application. The first thing you do is you destroy the database model, right? You carve it up in little pieces that you can manage. You carve up the monolith in small services that make up the application. And what you end up with is a distributed set of microservices which are all maintaining their own state. So even more services on platforms like OpenShift, backed by Kubernetes, will need persistent storage. So it's not just stateless anymore, right? And fortunately, OpenShift anticipated this need very early. So today we have a plethora of options available to connect to the existing storage services in whichever environment OpenShift is deployed in, to provide persistent storage for containers. So storage that survives the container failure and is available across multiple containers. And this is not a comprehensive list, but this is exactly what we support with the commercial version with OpenShift Enterprise. And that's already quite nice because it allows you to introduce OpenShift into an environment and connect to the existing storage service there, and then that's transparently provisioned storage to the user of the OpenShift platform. So they don't really see that this is essentially backed by NFS or Azure or GCE disk. However, taking a closer look at this, you'll notice there are subtle but important differences between all those storages offered here. And actually, as someone who's running the OpenShift platform, you would become knowledgeable in some of these quite well to make that work in a stable way with the OpenShift platform. So not all of these, or actually most of these, are not shared storage. They are storage services that you can only attach to one host and one container at once, right? The others that are shared storage sometimes have a single point of failure in their design. So they are not available throughout the entire environment. And some are even not dynamically provisioned, which means you as an administrator have to actually go in and pre-provision the storage. And you have to kind of anticipate what the developers will need in terms of capacity and features. And this is essentially where Gluster stands out, right? Gluster is storage that is shared, does not have a single point of failure, is dynamically provisioned, and is suited for the scale of storage requests that we are going to see in this kind of environment. So Gluster has a very mature integration in OpenShift, being able to dynamically provision volumes upon requests by the user. And it provides the ability to provide shared storage, so more than one container can mount that storage backend. And that is available since roughly 2 years now. And that's working fairly well. But we thought, what if we could basically make this experience, because Gluster is still external here, right? You still need to set up Gluster first. You need to read the admin guide, the installation guide, stand all this up. You have a little bit of a learning curve, and then introduce OpenShift to get to this stage, right? What if we could make this an out-of-the-box experience? So we introduce container native storage. What we do here is we take GlusterFS as software-defined storage, we containerize it, and we run it in pods on top of the OpenShift platform itself. Okay? So what we do is we co-locate the app pods with the storage pods, and essentially we are running GlusterFS like any other distributed application on OpenShift with native OpenShift management and orchestration, and running on top of OpenShift, meaning it runs on a higher level, on top of the infrastructure. It runs everywhere where OpenShift runs. So honestly saying at this point, when I first heard about this, I thought, oh my God, now we have gone completely crazy, right? What good is that going to do? I mean, this is a whole new concept of storage. What is this going to bring us? And I thought, okay, so this is going to be very complicated, so much technology stuffed together. Is this going to provide any value at all? It turns out my initial judgment was a bit off, because if you look at the storage services available to OpenShift closely, you see that this brings actually a lot of benefits. So why would you want to do something like this? The first thing is that you move to a new common denominator. So with GlusterFS running on top of OpenShift, you have basically this storage service available on any platform where OpenShift is supported on. That is bare metal in your data center, virtual in your data center, in the public cloud, and in the private cloud. It doesn't matter. So you have the same storage consumption experience, and you have the same storage management experience, no matter where OpenShift is deployed. OpenShift is our new base layer for this. And the storage behaves the same, and feels the same, and provides the same features no matter where we are deploying this. So you actually don't need to become an expert in any of these storages offered by these platforms. You just use container native storage, or CNS. The second point is that the way we do storage allocation and provisioning on container native storage is extremely efficient. So most of the existing storage backends for OpenShift come with one of two major drawbacks. The first one is that you actually have to pre-provision the storage. It's not dynamically provisioned. An administrator has to kind of guess what the users will need in terms of capacity and need to pre-provision these persistent volumes, as they are called in OpenShift, into a pool, and then the users will issue requests and will pick up these items from the pool. That's not really, dynamic or agile, right? That's storage management of the last 20 years. We don't want that. The other drawback that you find is that, especially on cloud provider platforms, the performance of your storage is actually tied to the provision capacity. So in order to get a certain minimum performance from your cloud provider backend storage in OpenShift, you have to actually reach a certain minimum capacity. So that is different with container native storage, because this is dynamically provisioned upon user request, and the full performance is available with the first gigabyte that the user uses. So we are not tied in terms of performance of provisioned storage with regards to the size of the provisioning request. And the third thing is that CNS enables a much simpler concept of application high availability. Many of these storage backends in OpenShift are actually not globally available in the platform. So when you deploy OpenShift and you deploy across several failure domains or AWS availability zones, the challenge you have is that the storage natively provided by these environments does not travel across these zones. It's stuck there, right? With container native storage, that's different, because the storage is available globally in the system. GlusterFS is based on replication and does that across these zone boundaries, and thus, no matter where your pods are running or how many pods are running, they can mount the storage wherever they are in the system. It's globally available and synchronously replicated for easier high availability. So you don't need to actually spend a lot of effort into getting database replication up and running or make certain replication concepts work at the application level. You can just count on the storage to replicate the data for you. So now you might think, I need to do a lot of learning and read up to actually get to this point. So let us start with the first demonstration of the technology here that shows you that this is actually fairly straightforward to deploy, and from an application developer perspective, easy to use. So I'm going to kick off a little demo here where we have an OpenShift environment, pretty vanilla installation. You see I've added layovers here to compensate for my German accent, so you can read along. But eventually, this is a standard OpenShift deployment, right? We only have 2 additional projects here. One is an example project where we will launch a couple of apps later, and we have provided a storage project. This is where we will deploy the storage services into. And both are currently empty. This is a deployment with 3 masters and 3 application nodes, and these application nodes have free storage. So the way we deploy this is via a simple command line utility, which automates the entire orchestration process of the environment. So only 2 kinds of information are needed for this utility. The first is the name of the project where you want to deploy the GlusterFS pods in. And you need to tell it where to find the OpenShift nodes and what kind of block storage they have available. So this is called a topology, and we are essentially in a simple JSON format telling that deployment utility where our OpenShift nodes are, how to reach them, and what block devices they have free to use for container native storage. And that's pretty much it. We feed this JSON file and the project name and a couple of initial credentials to the deployment utility, and that will kick off the entire installation process. So this will stand up all the Kubernetes resources needed to make CNS running and online. And that's automated, so you don't have to do anything. It will reach out. It will create the GlusterFS pods. You can see they spawn up just as normal application pods. And it will initialize the storage pool between these 3 pods. And it will also deploy a second component that we call HackHeady, which is actually an API front-end for Gluster that makes OpenShift able to talk to Gluster for provisioning purposes. And you see that's all done. After a couple of minutes, you have a fully functional storage environment on top of your OpenShift platform. Not next to it, not outside, natively deployed on OpenShift. So what happened here is that these pods were spun up as part of a daemon set. The pods are giving direct access to the host's block device and networking, so for optimal performance. And each GlusterFS pod or each OpenShift node in question runs exactly one pod. There's also the aggregating pod that runs the API frontend, and that is what encompasses container native storage at the very, very basic level. So not a lot of magic here, actually. So how would someone use this? So in the example project, the first basic thing you can do is you can request some storage for the system. So the way you do this in OpenShift is you issue a request for storage. We call this a persistent volume claim. So in the UI, you can actually select the CNS as a backend storage for this. In this setup, it's even a default. You give the request a name, so you can uniquely refer to it in your project namespace later as part of application templates. You set the access mode, which, thanks to GlusterFS, can be shared access, and you specify how much capacity you want. And that's it. You don't need to be aware of anything else. You submit this as a request to the system, and after a couple of seconds, the system provisions the storage for you and binds it to that request. So no reaching out to the administrator, no pre-provisioning by the administrator, simple and straightforward with native OpenShift utilities. So normally, as a developer, you don't really care about what PV is actually made of, but for the sake of presenting and demonstrating this, we're going to look at the PV in a little bit more detail. So on the OpenShift command line, you can query that storage that was just provisioned for you for a little bit more information. And you can actually see how it's made up. So with the OC describe command, we can just look at the storage we just requested, and we can see it's backed by GlusterFS. And we can even see the volume identifier that GlusterFS uses internally. So we can actually also look at that from the GlusterFS level. So we can log on to the GlusterFS pods and launch a terminal session and have the native Gluster management utilities available. So we are just basically SSHing into it in a glorified way in the browser. And with the Gluster volume list command, for instance, we can see that very volume that we've just saw on the PV level being present at the GlusterFS level. And we can query this volume for a couple of details, and we will see that this is actually a three-way replicated volume. So the three pods that we've provisioned earlier are all holding copies of the data that goes to this volume. So the volume is online, three-way replicated. So what happened to make that provisioned is basically when I clicked in the UI, create storage, a request was sent to the system. The system reaches out to the GlusterFS pods and asks them to create shared storage as a GlusterFS volume. And this volume is then represented internally in the system as something called a persistent volume that you can use as an application developer, or more commonly as part of an application deployment process. So what you normally would have is an application template that makes this request for you and would carve out the storage needed for the application. And that is the next example. So now let's use this capability with an application sample. OpenShift ships with a number of templates that have stateful applications that can use persistent storage. The one that we are selecting here is a basic Rails application that will incorporate a Postgres database. And this Postgres database will use persistent storage to actually store the database files. So in the template here, you can essentially already influence that request and say how much capacity this storage for the database shall have. So 25 gig in this example. And once you are satisfied with all the defaults, you can kick off the app creation here. And this will create a two-pod application with the Postgres pod mounting the PV. So we can see as part of that, we have already a persistent volume claim issued automatically. That was part of the template. And as soon as the Postgres pod comes up, it picks up this persistent storage and presents it to wherever the container is running as a local mount. And that's it. That's how you supply persistent storage for containers in OpenShift. The details are actually a little bit hidden, but first let's make sure this application is actually functional. So the application is a simple blog example. So what you do here is you enter some data in an article, you give it a headline and a body text, and then that article text will be saved in the Postgres database. And the Postgres database will save it on the persistent storage. So we already created an article, we create a command. So it's all listing fine, no errors. So apparently the database is working, and the database wouldn't be working if there would be no storage, right? So let's have a look at how this is actually saved in GlusterFS. Again, going back to one of the pods, we can look at the volume that was created in Gluster to back the Postgres database. And the information that we receive from Gluster will tell us where this data is actually sitting. So these paths here, this is actually the replication endpoint of each GlusterFS pod. This is where the data ends up in files, right? And it's three-way replicated. It means all of those directories across the 3 different pods, across the 3 different servers that we have, will contain the same data. And on the local pod, we can actually look at this because this is just a local directory on that server, right? So we can do an ls, and we can see there's some data in there. And we will see that's actually the data of the Postgres database. So these are the Postgres database files. So this is how it ended up being stored in GlusterFS as part of the dynamic provisioning that container native storage offers. And this is persistent, so this can survive a pod failure. So now we are going to actually go ahead and kill our database application. Yeah? In the real world, what might have happened is that the server crashed. So if you wouldn't have persistent storage, the data would be gone, right? Because it's saved with the pod, and if the pod is gone, the data is gone. So that's not an option for a stateful or any kind of database workload. So when the Postgres SQL pod is gone, all data inside is lost. So never store any kind of important information there that you cannot recreate easily. So it's by definition ephemeral. And when we now go back to the GlusterFS level with the Postgres pod killed, we can actually see that in GlusterFS, the storage is still there. The volume still exists, and all the data in the volume is still intact. So the database pod just needs to be recreated at some point somewhere else in the environment, and it will be able to pick this up and continue going. Okay, so easy to deploy. Unique features that you don't get with most of the other providers, out-of-the-box experience, and basically simplified availability concepts. This is what CNS brings to the table today. So Michael will show you a little bit more on the technical side, how that's actually working under the hood.
Yeah, thank you a lot, Daniel. So that's really tremendous demo. And I hope with all that exciting stuff, you're prepared for a little more boring session from engineering. So I'm going to talk to you a little bit about how that all works internally and yeah, what we're doing under the hoods. Okay, yeah, how it all works, right. So we heard this, CNS, and there are a couple of confusions around that. So what actually is CNS? So CNS is the way we are doing what Daniel just demonstrated. We are putting a Gluster into OpenShift in this what we call hyperconverged fashion. That means the storage is running as containers in OpenShift, providing this dynamic aspect of storage provisioning. One component that was mentioned is that Heketi component. It is kind of the high-level service interface on top of Gluster that is also deployed in this case as a container. It is just hiding a lot of the nitty-gritty details of the low-level command line interface that Gluster usually presents. You have all the control over the details with that, but with Heketi, you just request a certain size, and Heketi goes and figures it out for you. So we basically have this. OpenShift is taken as a given. Gluster is what we want to put into it, and Heketi is sitting in between. So let's look a little more detailed at the components, right? So I mentioned Gluster, but looking from the top, in OpenShift or even raw Kubernetes, we do have a couple of components that make this possible. So we have the so-called dynamic GlusterFS provisioner, which is a module in Kubernetes that calls out to our RESTful API that the Heketi software is presenting, and which then goes and lets Gluster create the actual volume for you. That's for the provisioning, for the creation of volumes. But about the mounting, we didn't talk about how the volumes are made available to the containers, to the application pods. So do all of them need to have the GlusterFS client utilities installed for mounting? No. So we have a GlusterFS mount plugin in Kubernetes, which does the following thing. When there is a persistent volume that references a Gluster volume, it is mounted. So assume on a certain OpenShift node we have an application container that wants to use this persistent volume. This mount plugin goes and mounts that on the host, right? So only the host needs the Gluster tools installed, which is by default on RHEL. And it's then just bind mounted into the container. So for the container, for the application container, it's totally transparent. It doesn't even know or need to know it talks to Gluster. So that's the mount plugin. These are the two components we're developing inside Kubernetes. And thereby, they're ending up in OpenShift. Heketi I've touched, and GlusterFS, yeah, we can have one or even multiple Gluster clusters. They are running in containers. We saw this tool running, the deployment, right? I mean, a lot of components and setting that up all manually is quite an involved process. But we have this tool. You basically just need to prepare the input. What are the IPs? What are the storage devices on the various nodes? You call this tool, assuming you have this OpenShift installation ready and set up. And then this just one single command, it rolls it out for you. So these are the components in a little more detail of container native storage. You may also hear the term container-ready storage, which is actually a precursor of this. This is the situation where Gluster doesn't run inside containers in OpenShift, but it runs outside of the OpenShift cluster, external storage. But the very same principles apply. It's just the mode of deployment. You need some hardware or VM space to run your Gluster. But then you have the storage. You can do the same dynamic provisioning with the same components. So it's just what we are focusing on today is this. With this great appeal, everything is running inside containers. You don't need to bother about external stuff. But if for some reason, performance, separation, whatever, independent scalability, you want to have it outside, that's also very much possible. Okay. Okay, and hey, this is all open source, right? So here are the upstream bits. We have created an upstream project in GitHub called Gluster Kubernetes, which kind of is the upstream-facing side of container native storage. It contains demos. It contains the CNS, or what we call the GK, Gluster Kubernetes Deploy tool there. These bits are all there, but ties it all together. We also have a couple of demos which are much more dry, much more command line than what you've just seen. I mean, I couldn't ever make it look that great, right? And so this is all to be found here. Heketi has its own space on GitHub. But it's actually, I like to see it as part of Gluster. It's really the high-level piece of Gluster volume management. And the components in Kubernetes I've been talking about are residing in the package volume GlusterFS directory underneath the Kubernetes main repository. And of course, here is the main home of the GlusterFS distributed storage system. Not listing Linux or Red Hat, Linux, etc. Okay, these are the open source bits. So you can go there if you have anything. You can even try the open source bits. You can file issues there, etc. And just for completeness. So we've heard a lot of the glossaries basically already mentioned. Just depending on where you're coming from, if you're coming from OpenShift Kubernetes, this is all known. If you're coming more from the storage side, the concepts are really, a pod is the unit where you deploy containers, one or multiple containers as a unit. We have this persistent volume concept. We have the provisioner, which is a concept in Kubernetes that creates these persistent volumes for you. We have the mount plugin, and then we have the persistent volume claim, by which a user can request storage to be created for him. A persistent volume claim is after it is processed and the persistent volume has been created. It's bound to the persistent volume, and this is the handle for the user to access the data. Usually, depending on some internal modes, the data, the storage exists as long as the persistent volume claim exists. When it's bound, it can be used in an application pod. And you have briefly seen these access types. They may be important moving forward. So read-write once is more exclusive access, even though it's not fully enforced and fully implemented. Read-write many, RWX, is the one where Gluster basically shines, because this is distributed storage that can be accessed from multiple hosts, multiple clients at the same time. And also read-only access is possible. Okay, and the flavors of provisioning, dynamic and static, we have mainly been touching dynamic here. And this is really the new thing, where Gluster's flexibility is so good. as Daniel mentioned, I mean, we have this whole raw storage available to Gluster. And especially, I mean, we can request a lot of storage in these cloud provider things and get it fast. But just we give it out in small slices. We don't waste storage. User just wants 2 GB, he gets 2 GB. He doesn't get 100 pre-provisioned gigabytes where 98 are just wasted. So that's it. And with that, let's look a little more into how this dynamic provisioning process works through the layers. I mean, this is a graphic going from the user to, excuse me, to the storage server and back. And I have it in really boring text. So going from left to right, the persistent volume claim is created by the user. The provisioner extracts the details. So the provisioner is actually detected by the storage class that is referenced in the PVC. The details on how to contact the provisioner is extracted here. So it goes to Heketi, tells it to create a volume of a certain size. Heketi then has possible multi-cluster under its control. It goes and checks whether it finds a cluster that can satisfy this request for, let's say, 50 gigabytes, which we saw earlier. If it finds such a cluster, it tells the cluster instance to create that storage. If that's successful, this is handed back to the provisioner. The provisioner wraps this volume into a persistent volume, the Kubernetes entity, which is then, it also references the mount plugin. This is where that happens, right? The persistent volume contains the information how it is to be mounted. And in our case, we, of course, enter the Gluster FS mount plugin, so that is mounted with Gluster FS mount type and on the host. So this is all then returned to the caller. The PVC is bound to the created persistent volume. And after that point, you saw it as bound. PVC is bound, you saw in the demo. So at this stage, it can be used. Before that, when the creation is not completed, you see it. There's the PVC, but it's not bound yet. It's not in the system. OK, so that was about how it really works. So what are we shipping in Red Hat Container Native Storage today? So there have recently been 2 important releases. But first, let's go to what are the main use cases. So we've seen this persistent storage for apps, right? Was presented with a Postgres and so on. So this is the very typical thing. But there's another aspect, which is infrastructure storage, specifically registry, but also maybe some logging or metrics collection, stuff like that. This more counts as infrastructure, not for the end-user applications. So because we have seen how the storage for apps works, and there's a new thing, the registry storage. So what is the registry? The registry is basically OpenShift's repository for container images. And yeah, by default, this is done with NFS. But we thought the flexibility and high availability of Gluster may be a really good thing for this. So what we did, we made it possible to run, to back-end the OpenShift registry with Gluster. So let's move on. There is the January release. This was kind of the big thing in the sense it added dynamic provisioning and it added this deployment tool, right? Also, at that time, we were first deploying Gluster as a daemon set. Gluster is tied to the nodes. So these are special pods. They're privileged. They're tied to the nodes on which they're running. They're tied to local storage. They're tied to network interfaces. So they're not moving freely. They're really infrastructure. And the daemon set is a good fit for that. So we did it back in January. And so we just had very basic scalability in the number of volumes that. So a 3-node cluster could be serving roughly 100 plus volumes due to several reasons. There is some algorithmic complexity in Gluster that has been fixed meanwhile. And there is a certain memory requirement because of the way how Gluster is implementing a whole stack of translators that implements the features. So that was January and CNS 3.4. So CNS is always chugging along with the OpenShift releases. So CNS 3.4 was building on OpenShift 3.4, OpenShift Container Platform 3.4, which it in turn is building on Kubernetes 1.4. So just recently, we released this CNS 3.5, which improved a couple of things over here. So CNS volume can now back the OpenShift registry. We have a documented process for this. This is not the end of the line, but this is what we offer here. We have improved day-to-day maintenance operations like replace or remove a broken disk and automatically figure out where to get new storage for that, etc. So that was a big thing, an important thing to be done. We enabled policy-based workload provisioning in the sense that assume you have different qualities of disks like SSDs or an all-flash SAN array attached to your OpenShift nodes, and you have some spinning rust. So we create one cluster that just uses the fast storage. We create another cluster that uses just the slow storage. You create two different storage classes for that, and all that is managed by Heketi. And now with this release, you can tell Heketi, okay, you create a gold or fast storage class, and you point it to the one cluster. You create a slow storage class, point it to the other, and then you give it to your users as an administrator, depending on what they need, right? I mean, you need fast storage, really explain, okay, here you are, take that storage class, and he gets it. So that's this thing. I mean, this is actually quite important. So also we added basic support and validation for snapshotting and geo-replication. So geo is missing here. So replicating the storage to different data locations, right? An external Gluster cluster, something like that can be done. And we already, even though that will be the big theme for the next release, we already have a quite significantly enhanced scalability in the number of volumes. So instead of 100 volumes, we can easily scale to 300 or even more volumes with improved algorithms in Gluster and with reduced memory requirements. So this is what's shipping right now. And before telling you what's coming next, we have Annette who can talk to us and explain, show us the reference architecture that Sayan was mentioning before. So thank you.
Hi, my name is Annette Cluett. Hopefully you can hear me. I wanted to point something out that hasn't been said yet too much, which is everything that Daniel showed you and that I'm going to show you could be done now, and it's completely available via a GitHub repo. It's also documented in the OpenShift reference architecture on Amazon Web Services. It existed, this reference architecture existed before a couple months ago, and then myself, Ryan Cook, and Daniel worked to update it with about 20, 30 pages of instruction on how to include CNS and also CRS, container-ready storage. So if you search either on Google or on our customer portal, you'll quickly find that. It's a very, very good document. And then within the document, it'll tell you how to get to the Git repo. In the Git repo, you get the scripts, Ansible playbooks, and what you're going to do with that is you're actually going to end up with an environment that looks very much like that. Everything that's outside of the yellow box will be deployed in the OpenShift environment. So you get 3 masters, 3 infras, 2 app nodes, all the Amazon resources to get into that environment. And then what's in the yellow box is an additional set of playbooks that will provision an additional 3 app nodes to with the ports open and everything for the Gluster and Heketi pods. So very cool, and makes it something that you can try. It's not going to get, you're not going to get it in your free tier on Amazon, but if you deploy it and then shut it down or something, it's not too expensive to try this out. So what I want to do now.
Pointer, laser pointer, maybe. Just the right thing.
Okay. So what I want to do now is start a demo here somewhere. And what I want to point out here is before we had CNS and after we have CNS. So as you see there, we have the app nodes, and things are going quickly. But those were 3 app nodes that were shown in the Amazon EC2 console. So what I'm going to do is I'm going to deploy an application. I'm going to provision a PVC from a storage class that was available before CNS. And this storage class and the claim are going to be done by you basically attach a volume to a EC2 instance in a particular AZ or availability zone, and then you create a storage class, and you see it's referencing an availability zone up there, right there. and you can give it that, and you can provision it. So the actual interface, how to do the PVC, looks all the same. The big difference is going to be here that is tied to that availability zone. And when we go and look at it's deploying it, sorry. When we look at how the pods show up in terms of where they show up in OpenShift, we're going to see a big difference between that when we have container native storage and when we don't. So it's come up. We've got the 3 pods running. It used the persistent storage via the storage class that we created. And we can see right there that it used that persistent volume claim. Now we're going to go ahead and just see that the application works. This is a very easy application. It's going to upload a file. In this case, the 3 pods will be able to read the file because they're all pointing to the same PVC or the same persistent volume. So this, is going to work similar as it would with CNS. We're going to see, though, the difference comes when we lose an availability zone. So we can see that it's there. And I just want to show real quick this. So just real quick on that, you see how all the pods are on the same app server? We have three app servers available in OpenShift, but they all ended up on the same one. They went there and they got created there because of that persistent volume claim that can only exist in one availability zone. So we continue, and as you might think, what we want to do now, because we want to show what happens if that particular node goes down. So we're going to take that node down gracefully via our EC2 AWS console. Take it down, and then we're going to look at what happens to our application. And again, just to stress, this was prior to CNS. This is the way that when Ryan did one of the prior version of the reference architecture, this is actually what was documented in the reference architecture. This was the way that you did it. So we look now, and what we see, these guys are hosed. They're not going to come up again. They can't come up because they have no storage in any other availability zone. So not only are they not able to, they can't recreate, so the application is down. If that storage was tangential to the use of the application, it's no longer available. So what we want to do now, from an OpenShift perspective, really it's exactly the same. We're going to do a PVC claim up here. Difference is when we select that storage class, like Daniel showed you, that storage class is pointing to a Heketi route, pointing to a cluster ID that gets it to a Gluster storage pool. And now this new PVC is actually a volume on Gluster. So we're going to edit our YAML file, go in, down here, just whatever name we chose for our persistent volume, edit it, save it. That'll cause the application to do a rolling update. We see that happen here. Now, anything that was on, if we hadn't lost our application, but this, when it does this, whatever was on the storage will be gone. But now we have a new storage persistent volume. So we're going to see that that works. And we're going to upload a new file. So we test the application. All is well. We've got it up and working. So I want to just highlight this again. So this is really critical here. I don't know if you remember. Probably you do. It wasn't very long ago. But when we did the first PVC, it forced the pods to home all to that one AZ. Now with this PVC, which is spread across the 3 availability zones via the Gluster volume, you see that each pod is on a different host. So that's a critical difference right there. So we move on and quickly get to the the next fun event, which is to fail. So we're going to fail the same availabilities under the same node. And we see now we're still up, still looking good. We see that we're recovering. So if we were looking at the CLI, we would see it was recreating the pod on one of the two app nodes that's left. We see down here, when it shows up, they're all running. So app server 1 down, 2 and 3 still up, pod got recreated. We go back to our application, which is functioning fine. Upload a new file. And not only when we see this, not only will we have the file we just uploaded, but we're going to have files that were uploaded before that, because we lost nothing. So that is the end of that demo. Thank you very much. And definitely check out the reference architecture and check out the GitHub repo that Ryan is the author of as well. Thank you.
We're not done yet.
Okay.
But almost. Yeah, so
It's time.
if you would bear with me for briefly.
Okay. I'll just stand over here.
Okay, so I'll try to be real quick. What does the future look like? We have many things on our roadmap. So one thing is we are listening very closely to what our customers or users are saying and asking. So scalability is always an issue. You want more volumes to be able to host it on such clusters. For some workloads, this read-write one support, the performance is not enough. For instance, Cassandra Elasticsearch is specifically not qualified for it, but we're working on a better implementation. And there's for some applications, there's a request for lightweight S3 object access. And of course, always that maintenance things, once the thing is running, is important. So what's the roadmap like? For the summer to autumn timeframe, we expect a greatly improved scalability. I think it needs to be qualified. We need the numbers, but I think we're going easily with a 3-node cluster to 1,000 or more volumes. So that means basically if you add more nodes, you can kind of multiply that number as well. Proper read-write one support with this Gluster block thing. For instance, not only removing disk, replacing disk, but replacing whole nodes, stuff would be single command things that we can trigger. Gluster as a registry backend, now it would be a native choice in the summer release. It will not only be possible to configure it manually, but this will be native with the OpenShift Ansible installer. And in the future, may even, if this works all out, may even get the default choice. So, and the lightweight object S3 support for applications is also coming, at least as a tech preview in summer. And the deployment will over time be integrated from the standalone tool into the OpenShift Ansible installer natively. So this is going to come. I have more details, but I think the time is up. So I'm not going to go into the details. If you want to know the details about these bigger things that are coming, the slides will be made available, I guess. So talk to us. I'm happy to go into details, but the time is up.